people in class like you and Hans who want to see that kind of stuff.
Yeah,
There
sure.
are people who don't, so I do a mix of both. Okay. So we're starting with
Let's take a picture.
yep. So we're starting into our study of symmetry. So a lot of the molecules you're going to see on here, I actually pulled from the Otterbein University website. So they have an example, and you'll figure out what this is as we go along, called point groups. So they have an example of each point group and its symmetry. They have easy molecules from water to complex organic and biological molecules, and showing you how the symmetry works in them. So you can really just go through them and figure out all of these symmetry elements. I find both of these websites to be extreme. Now, those first two are the same website. It's just one of them is the Otterbein site, and the other one is a direct link to the Symmetry Gallery. So, but then the ChemTube also has its own Symmetry Gallery, and you just play with it for a while. It'll show you all the symmetry elements and will kind of spin the molecule around for you. The Otterbein has a button on it, so if you bring up a symmetry element, hit the play button, it'll actually show you, it'll move the molecule through the symmetry element, so you can get an idea of what that means. All right. Symmetry operations and symmetry elements. The operation is, of course, it's what it sounds like. It's performed on an object, and symmetry means that when you perform this symmetry operation, the molecule is indistinguishable from its original configuration, and it's superimposable on its original configuration. Okay, so look here. You see two symmetry, and the symmetry elements are the individual axes, planes, points through which a symmetry operation is performed. Here, you see a C3 rotation axis and a sigma H reflection plane. Now we'll go through what all that means. H in the sigmas, your reflection planes are all sigmas, okay? The H means horizontal. So the C3, okay, that's a rotation axis. Look at that molecule. Try to intuitively tell me why it's a C3.
Why it's C3? Just because there's three things bonded to it?
Yeah. So you want to so the three identical species bonded to the central atom. You want to think of these rotation axes as going in a 360-degree circle, and that 3 means you reproduce the indistinguishable molecule every time you do 1/3 of that, so 120 degrees. So if you notice, if I rotated that 120 degrees, not only would it look exactly the same, but superimposable means I'd be able to lay it on top of its original configuration and it would match.
Right. So, but if one of those had something else other than a hydrogen,
it wouldn't be a C3. Yep. So if you had a hydrogen pointing the other way, if you had a chlorine on there, yeah, it could not be a C3.
I see.
And then, of course, the sigma H, the mirror plane. This one actually, there's different types of mirror planes. This one splits the molecule down the center. So you notice if you reflect each side of that molecule through the mirror plane, you end up with the exact same molecule again. Imagine the top going down, the bottom coming up. It's going to look identical. Okay, now let's just start talking about these axes. So all of your rotation axes are going to be a C sub n. So it's going to be, well, there's a bunch of them. Point groups can have C infinity. Remember we talked about like oxygen, the homonuclear diatomic, and it had a C infinity axis. That's because I could rotate it around that axis for infinity and keep getting the same molecule.
Right.
So you could have a sub of infinities. You usually have 2, 1, 2, 3, 4. A C1 is a very anti-symmetric molecule because you have to spin it all the way around just to get it back to its original configuration. So here is one you're probably familiar with. We have the ethene molecule. So there you see it's C2 principal axis. Now you're going to have to learn to identify principal axes versus other rotational axes. Okay. Now, all your sigma H's, your sigma V's, which V is vertical, you're going to see a sigma D, which means dihedral. These are all going to be like, you're going to label them H, V, or D based on the direction of the central axis. Now, let's see if we can figure out what that means. Do you see here how, so you still see this principal axis up and down. Now you see the other C2 axes there.
Okay. Yeah,
So,
it's also
yeah. So if I rotate it through any one of those, I'm going to get an identical molecule. The C2 axis, that's the principal axis up and down. If you have multiple equivalent axes of rotation, usually the principal axis will be aligned along the Z direction three-dimensionally.
Mm.
So if you're going, okay, well, which one is this? So you want to figure out how the molecule is oriented X, Y, Z, and not just randomly, but commonly. And then your principal axis is going to usually be oriented along that Z axis. Otherwise, your principal axis is the C axis with the rotation axis with the highest value of N. So if I had C2s and then a C4, the C4 would be the principal axis. Okay, so now let's talk about prime and double prime. So the prime and double prime in this case, we talk about that in terms of symmetry. Well, at least with orbitals. In this case, they're to denote axes that are equivalent, but they're different for the molecule. So if you notice, if I call the principal axis, again, the C2, okay, you notice how this axis cuts the molecule in a different way than this axis, and they'll provide two completely different rotations. So that means one of these, and commonly, let's see here. We do it the same way as sigma V. Let's just stay. So let's just do this. We'll put your reflection planes will work this way. So your single prime, your first prime, will go on the axis that cuts through a bonding angle. Okay. Your double prime will go straight down the center of a bond. But you notice these are all equivalent C2 axes, and they just are going to cut the molecule and rotate it in completely different ways. So we have to denote them uniquely. Sure. So here's a fun molecule. First off, look at this. Can you name this?
Okay. Cyclobutane?
Yep.
Okay. All right, I guess it has enes, doesn't it?
Yeah, it's cyclobutadiene. Well, cyclobutadiene is what it's usually called, but yeah, cyclobutene.
Oh, okay. Okay.
Mm-hmm.
Cool.
And why is it, so you're taking organic. Why would it be called cyclobuta? Well, buta is 4 carbons. Diene, why would it be called diene?
Because there's two.
There's two double carbon double bonds.
Yeah.
So naming is fun.
Yeah.
Now, you can actually have multiple axes incident on each other. So your textbook will say incident. Looking at this, what does incident mean?
Incident?
Mm-hmm. Two different rotational axes that are incident upon each other.
Like they're on top of each other?
Yeah, they're just right on top of each other. So see, your principal rotation axis is your C4. Because you notice if I rotate this 90 degrees, I get the exact same molecule back. But on top of that is also a C2. So you notice if I rotate it 180 degrees, I get the same molecule back. So you can have multiple rotation axes incident upon each other. Or I also took that word from the textbook, that coincide. So incident or coincide, they're right on top of each other. You'll notice that when you're playing with Otterbein, it'll say like a C4 and a C2, and you'll click both of them and you'll see one axis. You're like, well, where'd the other one go? Well, unclick one of them.
Okay.
Now we have a fun. So yeah, that was an organic molecule. So I was like, let's look at an inorganic molecule. This is the tetrachloroplatinate ion. All right. A lot of fun. So now you notice here, so the principal axis is of course the C4, and then we have these multiple C2s. Now, if we're going to be consistent, how do you want to prime and double prime these?
You said the prime cuts a bond.
Yeah, so we go prime there.
And then double prime goes through the molecules.
Double prime there. What do I do for the other two?
I guess they're also just prime and double prime.
So yeah, you don't have to come up with different notations. So the two double prime C2s are absolutely identical in what they do to the molecule. The single prime C2s are absolutely identical in what they do to the molecule. So you can have multiples of each one in the same molecule. So the first thing to practice is, of course, starting to try to visualize these. Because if I just gave you this ion and said, pick out all the rotation axes, you're going to have to start to visualize, well, where are they? How do they rotate? Because you're not always going to have these axes drawn in. And the more complex, like try to do symmetry rotations on a sugar molecule. They're in there, but they're always at like some odd angle. And as they rotate, and then atoms flip over, and then they end up right back. They're difficult. I don't think we're going to push quite that far right now, because you have to build this sense first. My professor in undergrad, he was like, "Let's just go for one of the complex molecules." He goes, "Do you see the C3 axis?" And I was like, "No." So he goes, "Well, it's right there, and then it rotates like this, and it flips the atoms." And then I was like, "Huh?"
Okay.
So,
but there will be like a center on all of them. Okay.
They're all there. If the molecule, well, C1s technically don't really have a center of symmetry. Mm-hmm. That's your most anti-symmetric molecule. Every molecule is a C1. So, but otherwise, yes, they will have a center of symmetry somewhere. It's not even that, but it's not necessarily on an atom. When you go to the Otterbein, you're going to see some molecules where the center of symmetry is in the center. Well, here, this is a good example. In the middle of a ring.
Middle of a ring.
Yeah. So let's look at this. Let's draw the xenon pentafluoride ion. On the diagram, let's mark the C5 axis. And the ion contains 5 C2 axes. Where are they?
So it's going to be like flat, and they're going to be like fanned out.
Yeah. So this is going to be flat. Now, so let's see. I tried to do. All right. So you have your xenon in the center. Now you're going to have 2 lone pairs. You remember with Vesper, the lone pairs want to be there. You consider them first, and they need to be as far away from each other as possible.
So like top and bottom.
Yeah. So that's going to be. Lone pair. Now, your fluorines are going to space out around the. Let's see if you remember your terms, around the radial positions.
The radial positions. So like, I mean, like they're going to be like perpendicular to the thing where the fluorines are. So
let's think of this: if the lone pairs are axial, where's radial?
It's just perpendicular to that, right?
Yeah. So they, if you think of it as they fit inside of a circle around, like flat around the center.
Okay.
So I don't know. I try to do it like I put a fluorine there, and then we're going to have fluorine there. Bring back our 3-dimensional representations with a vengeance. Now these you should be getting used to. You're an organic.
Yeah.
Okay, so can you kind of see how that's like flat around the center?
Yeah.
Okay, so in with your lone pairs up and down. Okay, so this is the molecule you're looking at. So where's the C5 axis going to be?
C5, that'll be like straight through the lone pairs, right?
Your C5 axis is there.
Right.
Now, what about the C2 axis?
Well, are they gonna cut through all of the fluorines?
So each fluorine is going to get a C2. It's kind of hard to draw like that. So I could draw that one like that. Oh, let's see. You end up getting a C2 there. I get these to go straight one through there. I'm gonna run out of colors. Like that. Oh, what else can I use? Yeah, that'll be fun. Then we have one. Through there. So it makes it look a little messy, but you get the idea. And so if you're trying to think of this three-dimensionally, your C5 is straight up and down. And then all of these C2s lie in the radial plane. So if you rotate around any of these, you just flip the molecule over and you get the exact same molecule back.
So would we call those prime or double prime? Because they kind of go like.
No, see, here's the thing. These are all just C2s.
They're just C2s
Because
they don't go straight down the barrel.
Right. If you notice, they hit a fluorine bond and then go between two fluorines, all of them. So they're all identical.
Okay, I see.
So they're not rotating this molecule in different ways. So they're all just C2s.
Mm-hmm.
All right. Well, let's look at some more. Among the following, why does only xenon tetrafluoride containing fourfold principal axis of rotation? So now we're back to our molecular geometry, which is fun. Let's see, CF4. These ones are hard to visualize. I'll try to draw it, but okay. So do you recognize that shape, CF4?
The tetrahedral.
It's a tetrahedral. So can you see anywhere in there where I would have a C4 axis? So fourfold principal axis. Fourfold means a C4.
Fourfold principal axis.
Mm-hmm. So anytime twofold, threefold, fourfold, C2, C3, C4. That's what they're talking about.
Yeah, if I just go down one of the bonds, then the other three?
Well, you might be able to get away with a C3 in that way.
Okay. Mm.
In fact, yeah, those are C3s. If you go straight down each bond, so if you imagine the molecule sitting like this, then yes, straight down each bond is a C3. Now there are C2s are a little harder to visualize. So let's draw it like this. More traditional representation. So two in the plane, forward and back, makes it easier to see that right here, there's a C2 axis, but there's really nowhere in there that you can put a fourfold rotation. Anywhere you try to rotate it by only 90 degrees, you're not going to get an identical superimposable atom or molecule back. Okay, well, let's look at the SF4. Oh, do you recognize that geometry? What is that? So this is so you can review this in chapters 1 and 2 because I didn't, because we did this in Gen Chem and they don't really go any deeper into it.
Yeah.
But it's your molecular geometry.
I can't remember the name of it, but it's got like lone pair.
Yeah, it does. This is your seesaw.
Seesaw. Okay.
Yep. So it does have a lone pair there. And again, you can look at this. You can definitely see the C2 axis.
Yeah.
And that's actually the only axis you have. So you can see a C2 axis, but there's no way to do a C4 axis.
Right.
Okay, well, the boron tetrafluoride ion, I need to look up the name of that. Some of these names are getting bigger and bigger. It's like fluoridate or something like that. But again, we're back to the tetrahedral, so we already know that can't have a fourfold axis. Okay, what geometry do you see from xenon tetrafluoride?
It's like planar.
Yep, and remember, so it has an octahedral electron geometry, so where are the lone pairs?
Top and bottom.
Top and bottom. Now, but here's the thing, with rotation axes, we don't consider lone pairs. We only consider the atoms. So if you look at that, where's the C4 axis?
Just straight down the lone pairs.
Now this one is going to have C2 axes. Where will they be? And how are you going to label
them? You'll have them like you'll have the primes in between them, and then the double primes going through them. So you have 2 of each.
There's one. There's one. This three-dimensional. Okay, so we can't make this look just like so we'll try to do it like that. It's going to come out the other side, kind of like that. And then, I guess that's good enough. Kind of splitting between those two. Yeah. So you have your principal axis of C4, then you have 4 C2 axes, 2 primes, 2 double primes. Okay, so that's a nice little intro into rotational axes. All right, symmetry planes. Okay, your sigma h is going to be a plane of symmetry perpendicular to the principal rotation axis. So you see again, we're back to this molecule where you see the C3 principal axis. Now, do you notice how the sigma h is perpendicular to that axis? And so your CVs will contain the principal axis, or you can think of them as parallel. So imagine a plane going around the other way, and the C3 is actually inside of it. Those are going to be CVs.
So it's going to have multiple of those, or is it just one that's?
Well, it depends on the molecule.
So maybe like on this one, it like cut down the middle of those bonds, each of them, or?
Let's see here. That's it. No, it couldn't. It couldn't, because if I cut down the middle here, let's say I cut down the middle there, reflecting that would put the hydrogen over here, which is not going to be the same. So this one is actually not going to have any CVs.
I see.
And then your D is your dihedral planes. And these are going to bisect 2 adjacent twofold axes. these will take some practice to get used to, because sometimes they're on C2 axes, but they bisect other C2 axes. It takes some getting used to. I'm going through this faster than I thought I would. Because I mean, what I have on here now is already like a little over a third of the chapter.
Well, I can ask you questions about my homework if we run out of things
Okay.
to talk about today.
Yeah, so I'll run and grab my little reference, so we'll make sure I'm telling you. Here we see, now here, okay, here you see your sigma v and your sigma v prime. Now, this is what I mean by containing the principal rotation axis.
Yeah.
So these are verticals. And of course, you see your sigma v cuts between the bond, and yours v prime cuts straight down the molecule. And so if you reflect through either of those, you're going to get the exact same molecule back. This hydrogen will come over here, that one over there. Or you're just taking this half over here and this half over here. You get the exact same molecule.
Right. Yeah, it's literally like putting a mirror there.
Mhm.
And they'll look the same. Okay.
Yep. Here we're back to our platinum compound. Now let's compare the sigma V's to the sigma D's. Okay, first off, yes, these sigma V's, and technically so, your C2 primes and your double primes, okay? The sigma V's do technically cut the C2 primes between each other. And so there's a tendency to call those sigma D's. However, when the planes lie right on the molecule like that, we usually call them sigma V's. Okay.
So the sigma D will go with the double primes, like it'll be.
Yeah. So in that case, first off, notice how the sigma D's cut through the angle, cut through the bond angles.
Mm-hmm.
So that's your first clue. And then they are along the primes, so they cut a double prime and a double prime. Okay. And so these will take some practice to get used to. So as I said, the primes are commonly set on the XY axis. So that's another way you can tell. So your C2 primes will commonly be along your coordinates. And so then if your plane lies along those same coordinates, those are usually your V's and not your D's. Your D, so think of it in terms of an XY axis. We can't get a whole plane because it's just 2 dimensions, but so if I cut like that, and I'm cutting between 2 C2 axes, then I have a sigma D. Okay. If I cut along either of the coordinates, you're looking at a sigma V. And really what these are just conventions that have been developed and adopted over the years. It's just helpful to know the lingo so that you can follow along.
Sure.
Okay. Now here's some interesting molecules. Here we have bromine dibromine tetra. Hang on. Oops. That didn't make sense. Boron. Sorry about that.
Okay.
So diboron tetrabromide. That's going to be your left one over here. Boron, bromine. And then you have your diboron tetrafluoride. They're going to be they're going to have these. They're similar, as you notice, but they take these different spatial geometries. So of course you notice that the bromines are twisted at 90 degrees to one another, and this one I put the Lewis structure up because it's a planar molecule. So show that the BR2, BR4 has one less plane of symmetry than the B2, BF4. Work on that for a minute. Let's see what you come up with.
Guess I'm trying.
Also, the B2, BR4 has two C2 axes. See if you can figure out where they are. This is something that was done to me in undergrad. So we're going to share the hazing.
Okay, cool.
This is one of those ones where you have to place it so that it flips the atoms while it's rotating.
Okay, so I should like do the axes and then also the planes?
Yeah, I just want to see if you can figure out kind of how the axes point.
Okay. Let's say. Let's
Can't be straight down the middle if you wrote. Well, no, actually.
That could be C2,
Yeah, it is.
right?
Yeah, you're right. Never mind. That's a
And
C2.
you said there's two of them?
Uh-huh. Well, actually, now there's three. I didn't account for that one.
Oh, okay. Um,
So if
can I do one like this way, like going into the screen?
kind of,
And then that would just be C2?
yeah. So kind of think of it like this. Let's see. Start way out here. I'm actually going to try to draw this. Kind of think of it like that.
Yeah. Yeah.
So as I'm rotating it, those bromine atoms are also rotating, and they fall right on top of the same spots.
Right.
And so then you would have a similar one going the other way. Okay. So then, of course, yeah. Thanks for finding what I didn't account for. So that one. Now, so here's the thing: if you're going on Otterbein to look this up, this, for example, is a D2D point group. So they're just going to have these lists of the point groups. This helps you find this one. This one over here is a D2H. So even though like this diboron tetrafluoride is not on Otterbein, you can still look up a D2H and get the idea. There is one on there that's very, very similar. It's that's the D2H they have on there. So you can see how the symmetry elements will be the same. Now, what about so let's see if you can find your reflection planes in the B2, BR4.
I mean, I'm finding one that's kind of like flat.
Yep. So we could say there's one.
And would that be sigma H?
Let's see. Well,
or is it sigma B? I don't know, because I guess it's parallel to them.
So here's the thing. Usually your z-axis is going to be along the main coordinate of the molecule. So, well, actually on this one, both of them are sigma Ds. It's kind of hard to see. But if I put one, now let's see how to do this. Let me try to draw this other. Okay, so there's that other similar C2 axis, okay? So let's say I draw in a plane.
Oh yeah, I see.
So I think to make this more clear, let me draw this one the other way. So I'm going to start down here. There we go. Let's draw it like that. So that way, so I can go back here. Oh, since this plane is going to go right through the center of those. And then I'm having issues. I'm not an artist. Okay. So you can kind of see how it splits those two.
Yeah.
And so since that's a C2 and a C2, that's a sigma D. Okay. Now, your other one, oh goodness.
Okay, so I can have like a.
It's going to be this. It's going to be the same idea, but rotate it 90 degrees.
Rotate it 90 degrees.
Okay, let's see here. Let's do this. Okay. It's going to go behind both of those. Oh boy. Going to go through both of those. It's in front. Okay, it's there. It's the same plane. They're going to be 90 degrees to each other.
Sure.
So since that also cuts those C2 axes, you get a sigma D. Again, I'm going to draw these the best I can. This is why I gave you the websites. It is going to draw them so much better. And you'll be able to look at the planes one at a time.
For sure.
Okay, so those are the only planes that we have in this one. The rotation axes on the B2F4 are easy, so just do the planes. Keeping in mind, that you have, let's put your there's your principal axis, okay? No, let me not do that. I'm gonna confuse you. Just find the planes because in a D2H they're all sigma V's.
Okay. That would be. I guess I can do that.
Oh, you're working on that. I want to do this. Sorry. Sorry, I won't be able to see this on the Zoom, but I'm going to try to find this otter bite. Because it'll be much better than me drawing it. Yeah. Symmetry gallery. So see here you have all your options, all your different ways to study.
I see.
Symmetry challenge, the gallery, the tutorial, and then of course this is the D2H. So here. We could look. Oh, no, they have ethylene. That also works. Okay, cool. They have that one. There's another D2H. So let's look at this one. This is the most. So if you look here, you see how you have a C2 that's going straight in and out?
Yeah.
So now watch this. If I do that. Oh, hang on. See the symmetry?
Yeah.
Then I have a C2 there, one there. So it has all three of those. But all three of these are sigma V's. So where do you think they are? Let me see what you got.
I have like flat, like
Yep.
the bond. I have one that goes like cuts.
Oh, you got them. You got them all. So let's see. We have one there. on there. So you see a reflection.
Right.
Then you have that one. So again, just to kind of, let's see if I can put this on, make an attempt to put this on the Zoom. Okay, so the first thing I want to do. Okay. Goodness. I need to talk about a plane being, so the molecule lying in the plane. That way it's just going to reflect forwards and backwards.
Right.
Okay, now I'm going to have one. Try and do some cutting and pasting so it doesn't get really long. When I have one there, that's going to reflect one side, the right to the left and the left to the right. Okay. And then, like you showed, I'll have one there, which is going to reflect top to bottom, bottom to top. So if we're able to pick out the planes, you can see that this one does in fact have one more symmetry plane than the D2D molecule. Ah, where did my how to put that molecule on there? Okay, now something kind of fun for you. Oh, okay, so this is like your ethane molecule. But here's something from organic. Have you learned this yet?
ZD.
ZNE.
Yeah, same side and whatever the E
Same
said.
It
Yeah.
would. So if I have, so the C's of course are central.
Yeah.
Yeah,
That's what Dr. Keithley told us.
yeah, but it's true.
It's true.
It's true. But okay. So your Z high priority substituents are cis. E high priority substituents are homo. Okay.
Yeah.
Cis and homo. So okay, so let's do your Z configuration. Which one, H or F? Which one is going to be our high priority?
That.
The F. So they're going to be cis from each other.
They're going to be same
They're
side.
going to be opposite side. There you go.
Okay, opposite side.
Same side, and opposite side.
I like it.
Okay. Very good. Okay, so F, H, H. So this is our Z configuration. Let's look at our E configuration. Doesn't matter if you draw them up or down. You have the same symmetry elements. Okay, how do the rotation axes and planes of symmetry differ between these two?
Okay. Wait a minute, let me think about that. I mean, for when they're trans of each other, you can do one more rotation. Like if I'm looking at it top down, I can do like C2. Whereas if they're
So
I can't.
C2 like that.
Yeah.
Okay, well, but there is a C2 axis in the E configuration. Where is it?
Or is it just like if I look at it? No, that's not right.
Don't make this too hard.
Just like this way?
Yeah. So if I put I can rotate like that. Now, what about reflection planes? Do the E first because it's the easiest.
Reflection planes. I mean, you can just go like right down the middle. Like cut that double bond in half, right?
Oh, hang on. Did I put those in the right place? C is cis. Ah, darn it.
Uh,
Oh, and it's not homo, it's trans. Okay. I'm an idiot. Okay. I did these backwards. Z is cis, so I'm thinking of homonuclear that got in my head.
oh,
Okay. Let's do this again. Cis. The S are on opposite sides. Okay, so that's no, they're on the same side. Damn it. It's gonna be a day. Okay, so this one's your E, this one's your Z. So let's review that again since I messed it up. Your E,
E has the top down, and then Z has the cutting through. I guess they both go through the double bond, but
so trans, opposite. F will be cis, same side. Now it's correct.
yay.
Okay, so do the go to the Z. Do now that we know which one the Z actually is, go and do the symmetry plane.
Okay, I'm gonna say that it's gonna be like right up and down.
Yep. So there's only one plane. It's going to cut like this. It's just going to reflect front to back, back to front. So it's cutting right through the atoms like we've seen before.
Can I not put one like this way?
You actually, let's, oh yeah, you can.
So it has two then?
Yeah.
Okay.
My notes are backwards. So then there's going to be one here. Well, sorry for whoever's listening to the.
That's okay.
We got it right eventually.
They'll figure it out.
We got it right eventually. Now, what about the E configuration?
This one just has the one.
Right. That's why I wanted to say the other one had the one because it's backwards for my notes because I messed up Z and E the first time. Okay. So we're out of time today. We'll continue on with this next time. Hopefully, I'll read my notes better.
Yeah, okay.
So I got homonuclear stuck in my head. Like, no. Z and E are cis and trans. Cis and trans.
Okay. Yeah. That's okay. I'll figure out too.
All right.